Sorry, I need to watch the time on these. The maximum time it lets me record is 15 minutes, so I'll try to watch that better. So this map is a map of the H2 regions, which they actually map it with carbon monoxide because that's easier to detect, and they accompany each other, so it's easier to use that. So molecular clouds are very cold, 10 to 50 degrees Kelvin. So remember, 0 degrees Kelvin is absolute zero when atoms and molecules do not vibrate. They're frozen completely still. So that's very cold. They can range up to 300 light years in diameter. The hydrogen in them cannot be detected directly, but by tracing that carbon monoxide. The Milky Way contains 1,000 to 2,000 giant molecular clouds in addition to smaller clouds. They have the mass of 100,000 suns and can be 300 light years in diameter. Sorry if some of these words get cut off. I can't really fit the recording without cutting a few of the words off. So there's a picture of the Milky Way in infrared. And this should look pretty familiar to you, kind of an edge-on view where the sun is and a bulge. It's pretty much exaggerated because the bulge isn't a perfect circle like that. But out in the outer areas are those globular clusters that you made in marshmallows. So our solar system is actually tipped within the Milky Way. So it's at an angle of about 63 degrees from the plane. And then the Earth again is tipped again. So our 3D model of this is different than you might have imagined. So we know that globular clusters look like these giant snowballs of stars, and that those are located out in the halo of the Milky Way, not in the disk. And then we have galaxies that we can see farther off, and these are not part of our Milky Way, but we can see them with our telescopes in the distance. So, I don't know if I can move me. Maybe I can. No, I can't really very well. So these little drawings are trying to illustrate, we're trying to figure out how these spiral arms form and how do they stay in a spiral shape over millions and billions of years. The regions farthest from the galactic center take longer to complete their orbits and thus lag behind the inner regions. So that makes sense. The outer stars have to travel farther, so it takes them longer to go around. If this were the only mechanism for creating spiral arms, then over time the spiral arms would completely wind up and disappear. Since many galaxies have spiral arms, they must be long-lived, and there must be other processes at work to maintain them. So that's kind of a picture of if you dropped a couple of blobs of cream in your hot chocolate and you stirred it, eventually it would stir up and stir up and stir up till the spirals would end. They would mix together. And that's not what happens in a galaxy, so that's what they're trying to figure out, is what the mechanisms are for this. So in Kepler's law, we remember that the planets that are closest to the sun have a harder or a stronger gravitational pull, and therefore they travel faster than the planets that are farther out. So they orbit much quicker. Not only do they have less distance to travel around, but they actually travel faster. Their velocity is faster. We expected that to be the same case with stars. We expected that stars farther away from the central bulge, where the majority of the gravity is, that they would get slower and slower and travel slower as they move out. But as you can see on this graph, the lower red line is what we think it should be like. That's what Kepler said. That's how the planets are. That's what we expected. But when it was actually measured by Vera Rubin down in Kitt Peak, she discovered that once you get a little ways away from the nucleus, that the stars, no matter how far you go out, all seem to be traveling at about the same speed. And this was a really big surprise. So here's a little diagram of the speeds. You've got the central bulge. Things are traveling a little funky, but once you get out to where they're traveling 200 kilometers a second, they keep traveling at 200 kilometers a second, farther and farther and farther and farther out. So here's another example of the cream in the coffee cup thing, and trying to figure out why we have these spiral arms and why they are acting the way they are. So this is what we think is going on. We think that there is what's called a density wave, and we liken it to a freeway. And there's road work going on the freeway where that orange triangle is. And as the cars are traveling along, minding their own business, they get to where the road work is, and they bunch up. And they have to travel a little slower where the road work is because they're all bunched up like that. And then as they get past the road work, they can continue on their way going the same speed limit. So what we're seeing is there is a place where they bunch up. In these spiral arms, the stars bunch up. Now, this is a really interesting diagram. It's not pretty, but look at it real closely. So where it says incoming clouds and stars, okay, so they're traveling along, and the stars or the gas clouds that are up there traveling along, minding their own business, and they hit one of these density waves. And where it's crashing in, where it says compression, that's where it hits the density wave, and whenever you start smashing gas together, you start getting star formation. So we see that there's star formation starting as it crashes into the density wave. Stars form. They're still moving through the density wave, but only the smaller, longer living stars make it out the other side. The great big blue hot ones and the big white hot ones live their whole lives in that density wave and die before they escape. This is the theory, and we do see that. We see that in real life. When we look at pictures of galaxies, we see an edge where it's lit up with new stars, and another edge where it's darker, where only the small red stars are existing, coming out the other side. So, how do density waves form? Well, we think they kind of the galaxies started like the image on the left side, where the stars are traveling around and around in elliptical fashion, but pretty much in their own row. But something happens gravitationally to tweak those ellipses. It could be another galaxy influencing it with its gravity that's nearby. Something tweaks it, and it starts making the orbits of the stars more condensed, and therefore a buildup, and therefore spiral arms are formed. Okay, so we just mentioned that the stars are traveling at pretty much the same speed the farther you go out in the galaxy. The only way we can explain that is by saying there has to be some gravity influencing those stars on the outer side of the galaxy as well as in the central bulge. Somewhere there has to be gravity, and we can't see it. We can't find it. We can't detect it with any detectors. So they've invented the theory of dark matter to explain this. And they say that dark matter completely envelopes the galaxy. Look how far out they're drawing that. Galaxy is inside, the halo's there with the globular clusters, and the dark matter goes clear out beyond. And the only way we detect it is through its gravitational influence. So within our galaxies, we have two types of stars. We have the population 1 stars, population 2 stars. The population 1 stars include stars with a wide range of ages. While some are as old as 10 billion years, others are still forming today. For example, the Sun, which is about 5 billion years old, is a population 1 star. But so are the massive young stars in the Orion Nebula that have formed in the last few million years. Stars consist of 1 to 4% heavy elements and are found in the disk. So the clue between these two types of stars is how many heavy elements are in them, or what we call metals. And anything more than hydrogen and helium we call a metal in this context. So the population 1 stars are younger. They have inherited metals from exploded older stars, so they have heavy elements in them and can form planets. Population 2 stars, they are older. On the other hand, consist entirely of old stars that formed very early in the history of the galaxy. Typical ages are 11 to 13 billion years, can have less than 1/100th of the metals found in our Sun. Found everywhere in the galaxy, disk, halo, and globular clusters. So you can remember population 2 stars are older because a 2-year-old is older than a 1-year-old. So we have the central bulge, which we talked about being a spiral, or a barred shape. And within the central bulge, we have detected a black hole that is about the size of 4 million suns. As we approach the center of the galaxy, we find the supermassive black hole Sagittarius A. There are also thousands of stars within a parsec of Sagittarius A. Most of these are old reddish main sequence stars, but there are also about 100 hot OB stars that must have formed within the last few million years. There is as yet no good explanation for how stars could have formed recently so close to a supermassive black hole. Okay, I'm going to move me over here. Perhaps they formed in a dense cluster of stars that was originally at a larger distance from the black hole and subsequently migrated closer. So that's kind of amazing when you see all of what's going on in the center of our galaxy there. So as much as 4 million suns, and we can calculate that by the motion of the stars around the black hole, how fast that they're orbiting. We can calculate how much gravity is being pulled, how much mass is within that black hole. So that leads us to the question of how did these galaxies form? So one of the very first theories was that it was a monolithic collapse. In other words, a huge, giant molecular cloud condensed down, and as things were spinning around, the globular clusters formed in picture 2 there. And the rest of it started spinning into a disk. We saw that with the solar system formation, that we got a disk, which is the natural physics of angular momentum to form this disk. And then eventually we ended up with the picture on the bottom right, where we have a disk, a central bulge, and globular clusters orbiting. But we don't see that really in space. So we think that the Milky Way actually formed from multiple mergers of galaxies. So there's evidence for this. For one piece of evidence is that the Sagittarius dwarf galaxy, which was only discovered in 1994, is on the other side of our Milky Way, which is why we couldn't find it for a long period of time. And it is currently merging with our galaxy right now.